Okay, thanks for inviting me this wonderful conference, and especially I appreciate the Professor Jaebom Lee from CNU for these invitations. My name is Dongmyeong Shin, and I'm currently assistant professors of the mechanical engineering of Hong Kong U. I'm very sad that I couldn't participate the conference in person due to the COVID-19 outbreaks. I hope we could get it together in the near future and discuss the science in person. Today, I'm going to talk about one of my research interests. My research interest has been focused on the energy harvesting as well as energy storages, especially the energy convergence from the mechanical energy to the electrical energy and the energy storage with all solid-state batteries. I'd like to briefly present my recent efforts on the energy harvesting from mechanical resources. The development in the electronics has been miniaturizations and portable so that it lead to require the tiny scale energy for powering the small electronics, making it possible to utilize tiny energy about micro to the milliwatt to power the electronics. This is newly emerging field of the nano energy, which is defined as the energy requirement required for the sustainable and maintenance-free and self-powered operations of the micro nanosystems. Even though the power consumptions of each electronics decrease, the electrical energy generated from the power plant is expected to not fulfill the demands. So we need the alternative for the powering the device beyond plugging all the devices into the grid. My main idea is the future powering technology is self-charging or self-powering. In these concepts are from the renewable energy research such as the light and the thermals and mechanical energy. We can harvest the electrical energy by harvesting the device. And then we save it in the storage devices to supply the stable output to electronics. So we don't need to plug it into the grid anymore for the small electronics. So among the variety of the renewable energy research, I'm focused on the mechanical energy because mechanical energy is a ubiquitous source that can be always reusable in our surroundings. So it can be on flowing water or wind on human motions. Now the question is, how do I harvest the mechanical energy? So we have used the piezoelectric and triboelectric nanogenerators, which are able to supply the micro to the milliwatt per centimeter scale from the each movement. The piezoelectric nanogenerators is an energy harvesting device to convert from mechanical energy to the electrical energy using the nanostructures piezoelectric materials. We utilize these nanostructures to harvest a small scale energy, so it names nanogenerators. Basically, the nanogenerator consists of the piezoelectric nanomaterials and two electrodes. When you apply the pressures, the polarizations will induce in these materials. Then the piezo potential induce the transient flow of the electron in the through the external circuits. And then once stress is released, the balancing of the piezo potential with the inverse flow of the electrons through the external circuits. The piezoelectric nanogenerator can be sensitive to the tiny movement by utilizing the nanostructures. In this effort, I've tried to use the novel nanostructures, including the inorganic and organic materials to improve the output performance of the piezoelectric nanogenerators. My interest was in improving the power output of nanogenerators. My first try to improve the power was doubling the number density of the nanorod in a given area. In the nanogenerator, each nanorod acts as an electron pump so that we could get double current if we double the number density of the nanorod. I developed this method to grow the zinc-oxide nanorod on the both surface of the graphene. And then to demonstrate the utility of the double nanostructures, so we built the nanogenerators. Here, the graphene acts as a middle electron load, so it can contribute to collect the electrical energy from the both top and bottom electrode. So when we apply the force of 15 newtons to the nanogenerators, the output current density was successfully improved by the twofold compared to that of the single nanostructure-based nanogenerator. The second approach was utilization of the biomaterial for the nanogenerators. The nanogenerator will be mounted or implanted in the body to harvest the energy, so that the biocompatibilities and toxicities are crucial for the practical approaches. So my approach was the utilizations of the biocompatible materials, which has a piezoelectricity for the nanogenerator applications. So we demonstrated vertically aligned M13 bacteriophages through the M4 infiltrations. Then we constructed the piezoelectric nanogenerators using the vertically aligned phases in the post template. The maximum peak powers of the nanogenerators was 0.99 nanowatt, and then we successfully light up the liquid crystal display using our nanogenerators. So when the device, including the piezoelectric material, is banded, the electrical polarizations can be driven by the piezoelectric effect as well as the piezoelectric effect. The piezoelectric effect is the polarization induced by the strain gradient in the device. So in the our listen works, so we try to distinguish the different polarization effect in our device. As you can see here, at the bending state, the voltage and generated charge are greater than those of the compressing state, even at the same effective stress. We assume that this excess charge coming from the piezoelectric effect, and we found out 10 to 20% of the electrical charge is induced from the straining gradient. In the previous work, so we successfully extracted out of plane piezoelectric contribution, which means the distractions. Then how about the in-plane piezoelectric contribution in the electrical distractions? I mean, along the surface. So we fabricated the horizontally aligned piezoelectric nanoroll, and we can decompose the in-plane the piezoelectric contributions with half of the quadrantine electrode, which account for 12 to the 20% of the overall electromechanical output. The next, the triboelectric nanogenerator is an energy harvesting device based on the triboelectricity. Let me briefly explain about the working mechanisms of the triboelectric nanogenerators. So when you contact the two different materials, make the contact between two different materials, electrons on the material surface can transfer due to the work function difference. And then after separating these material in close proximity, charge separations induce the polarizations between the materials. So if we connect the axial circuits to let the electron pass through, so we can harvest the energy. So in my effort, I will try to develop the wearable triboelectric nanogenerators. At the initial stage, I focused on the development of the flexible nanogenerators. In this study, the nanogenerators are categorized into the two different architectures according to the structural design options. The first is the airflow-driven fluttering membrane, and the second is a rubber vibration-driven fluttering membrane. Here, second one and first one. For the top nanogenerator, first one, the fluttering membrane can float in the middle between the top and bottom electrode and correspond to the mild the airflow. In this geometry, the working distance of the fluttering membrane is listed by the space between top and bottom electrodes. The key features of the second design options are placing the elastic rubber belt between the two separated the fluttering membrane, so that we could expect the synergetic effect between the aerodynamics and aeroelastic motions under the strong wind. So another one is the washable and breathable and wearable triboelectric nanogenerators. Polyurethane nanodot patterns on the Gore-Tex fabric act as an active material for the triboelectricity. The gold electrodes was deposited on the other side of the Gore-Tex. If we make the lubbering between these nanogenerators and the other fabric, we could harvest the electrical energy. For the practical demonstrations of these nanogenerators, we attach it to the outdoors spatial plank, so that the nanogenerator can harvest the energy through the frictions by a arm swing motions like this. These results suggest that our nanogenerator can be applied to the versatile closed to generate the triboelectricity through the frictions of the various types of the material surface. So one of the main issues in the triboelectric nanogenerators is the durability as a working mechanism is based on the physical context and physical wears. So our approach to improve the durability while maintaining the output performance is using the brush. The brush has a high elastic property so that it could be deformed under mechanical stimuli, and therefore it can enhance the contact area as well as durability of the contact electrification layers. Indeed, we have decent output in multiple working mode, and we are able to operate the EMG modules using the TNG, and we can charge it the capacitor, and we can light up the 100 LED using TNGs. I'm also interested in some fundamentals in the triboelectric nanogenerators, so that my student Ma is working on elucidating the charge transfer at the interface in the triboelectrifications. This is not published work yet, so that I can't say about the details, but he found the trade-off point where the electrons and the ion transfer are crossed over, so as the function of the durability. So the reason why we are interested in this fundamental stuff is the understanding the basic charge transfer mechanisms will open new chapters of the triboelectric nanogenerators and give us the design rules for the next generations on triboelectric nanogenerators. So then my student Ju is working on the very challenging stuff, so which is electrified triboelectric nanogenerators. Intrinsically, the triboelectric nanogenerators the AC signal, since the charge accumulated should be coming back. So but he developed the electrified triboelectric nanogenerators without any external circuit based on the dielectric breakdown theory. So here is quite promising his preliminary result. So top one is electrical output from the typical TNG. So they have some positives and negative signals, and the bottom one is output from the his device. Indeed, there is no positive signals; they only have some negative signals. So indeed, it is electrified. Now it's time to wrap up. This is my journey to develop the self-powered electronics. I have developed the main component of the self-powered electronics, which include the energy harvesting and energy storages and bio-inspired sensor devices. As part of my journey, I introduced the piezoelectric and triboelectric nanogenerator that are promising for the next generation wearable energy harvesting devices. So moving forward, I will work on to build for the performance of each component, as well as to integrate them in the device as a self-powered live chips. I really appreciate my team at Hong Kong U. Also, I'd like to thank my all collaborators in Busan National University and Hong Kong U. And lastly, I appreciate the financial support from the Hong Kong U and the Research Grant Council of Hong Kong and Environmental and Conservation Fund in Hong Kong. Thanks for your kind attention. And due to the time limitations, I went rush and skipped some more details. I'm happy to take up any questions and comment. So this is my the email address. So feel free to reach out to me if you have any questions or comment. And many thanks for your kind attentions.